Forget black holes. Forget gamma-ray bursts. Forget supernovas. The single most dangerous, reality-breaking, and terrifying thing in the entire universe is the empty space in your coffee cup. That slice of nothingness you're staring into? Our best, most tested, most successful theory in all of science calculates that it should be seething with a hidden energy. An energy so colossally powerful, so violently repulsive, it should detonate the fabric of reality itself, tearing you, your cup, your planet, and the entire galaxy to shreds in less than a nanosecond. So why are you still here? Why is our universe expanding with a gentle, almost lazy, persistent push instead of a cataclysmic explosion? Because somewhere in our understanding of the cosmos, we have made a mistake. An error so enormous, so mind-shatteringly wrong, it has been called the single greatest failure in the history of theoretical physics. Today, we are opening the books on reality itself. We're launching a full-scale audit to find out why the math is off by 120 zeros, and what the eerie silence of the vacuum tells us about our own impossible existence. First, let's examine the evidence. For most of the 20th century, the story of the cosmos was simple. The Big Bang happened. The universe is expanding. And gravity, the universe's great sculptor, is acting like the brakes, relentlessly pulling everything back together. Would the universe expand forever, slowly cooling into darkness? Or would gravity eventually win, pulling everything back into a fiery big crunch? That was the debate. Then, in the late 1990s, two rival teams of astronomers set out to settle the question. They used the Hubble Space Telescope to hunt for the most distant, most ancient explosions in the cosmos, type Ia Supernovae. Think of these supernovae as the universe's standard issue, 100-watt light bulbs. They are the result of a white dwarf star, a dead solar core, stealing just enough matter from a companion star to push it over a critical weight limit, exactly 1.44 times the mass of our Sun. At that precise point, it detonates in a thermonuclear explosion of predictable, uniform brilliance. Because we know their intrinsic brightness, we can tell exactly how far away they are by measuring how dim they appear to us. Day after day, night after night, these teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, collected their data. They expected to find that these distant lighthouses were slightly brighter than predicted, indicating that the universe's expansion was slowing down as gravity took its toll. The results that trickled in were baffling. Impossible, even. The distant supernovae weren't brighter. They were consistently, undeniably dimmer than expected. They were much, much farther away than the standard model of cosmology allowed. Something was wrong. For months they checked for errors. Dust? Telescope miscalibration? Some new kind of supernova? Every alternative was ruled out. The conclusion was inescapable, and it would win them the Nobel Prize. The brakes on the universe weren't working. In fact, they weren't brakes at all. For the last 5 billion years, something has been stepping on the accelerator. The expansion of the universe isn't slowing down. It's speeding up. This wasn't a one-off finding. It was a conspiracy. Astronomers looked at the universe's baby picture, the cosmic microwave background, the faint afterglow of the Big Bang. In the subtle temperature fluctuations of this ancient light, they saw the fingerprints of this same accelerated expansion, encoded in the very geometry of space. They mapped the cosmic web, the magnificent, galaxy-strung filaments of matter stretching across billions of light years. They saw that the growth of these massive structures had been gently stunted, as if gravity's relentless pull was fighting a losing battle against a persistent, invisible push. Every clue, from every corner of cosmology, pointed to the same bizarre culprit, an invisible energy woven into the fabric of space-time itself. A property of the vacuum. We gave it a name, dark energy. And the simplest explanation that perfectly fit all the data was an idea Albert Einstein himself had proposed in 1917, and later abandoned, calling it his biggest blunder. A cosmological constant. A fixed, uniform energy density of empty space. Its codename, lambda. So what is this cosmic ghost? How does it behave? Physics can actually describe its personality with a single number, a letter called W. All you need to know is that W is the ratio of a substance's pressure to its energy density. For normal matter, like the air in your room, W is positive. It has positive pressure. It pushes outwards. If you put it in a box and shrink the box, the density goes up. Simple enough. But for dark energy, the astronomical data screams with near-perfect certainty that W equals -1. This means it has negative pressure. What on earth is negative pressure? The best analogy is tension. Imagine the fabric of space-time is a giant, stretched rubber sheet. A gas in a balloon pushes everything apart from the inside. But the tension in the rubber sheet itself pulls everything outward as the sheet expands. It's not a push from a point, it's a pull from everywhere at once. This tension is an intrinsic property of the space-time fabric. And here's the weirdest part. As the universe expands, and the volume of space gets bigger, you'd expect the density of this energy to go down, right? To get diluted. But it doesn't. Because W equals -1, the energy density of the vacuum remains perfectly, stubbornly constant. As space expands, more space is created, and with it, more of this dark energy comes into being from nowhere, maintaining the exact same density everywhere and for all time. And the amount of this cosmic tension? It is fantastically weak. The measured density is about 6 billionths of a joule per cubic meter. Let me try to put that in perspective. A single grain of salt, if you could convert it perfectly to energy, contains more power than exists in a cube of empty space 1,000 kilometers on each side. It is the faintest whisper imaginable. But, and this is the crucial part, you spread that whisper across the entire observable universe. Suddenly, the combined tension of trillions of cubic light-years becomes a gale force wind, an unstoppable force driving every galaxy apart from every other. So, for a moment, the story seemed complete. A beautiful narrative. General relativity provides the theoretical framework. The astronomers provide the startling evidence. The puzzle of the accelerating universe seems solved. Case closed. And then the quantum physicists walked into the room, took one look at the answer, and their faces went white with horror. Because the number that cosmology had celebrated as a discovery, quantum physics viewed as a declaration of war on reality itself. To understand the crisis, you have to appreciate the staggering success of our other pillar of modern physics, quantum field theory, or QFT. This isn't some fringe idea. It is the most precise, most stringently tested, and most outrageously successful scientific framework humanity has ever conceived. Its predictions for things like the magnetic moment of the electron have been verified experimentally to an accuracy of 1 part in a trillion. It's like measuring the distance from New York to Los Angeles, and getting it right to within the width of a single human hair. QFT is the bedrock of our understanding of particles and forces. And it tells us, in no uncertain terms, that your idea of empty space is a childish fantasy. It's not empty. It's a bubbling, fizzing, frenetic cauldron of activity. Every fundamental particle in the universe, photons, electrons, quarks, the Higgs boson, is not a tiny dot, but an excitation in a universe-spanning field. And these fields, even in their lowest energy state, a state we call a perfect vacuum, can never, ever be perfectly still. It's forbidden by the Heisenberg uncertainty principle. There is always a residual hum, a fundamental vibration of existence. This is called the zero-point energy. Imagine an infinite orchestra, with an instrument for every particle in nature. Even when the orchestra is silent, every string on every violin is still gently vibrating, every column of air and every trumpet is humming. Add up all that background humming, and you have the energy of the vacuum. A more dramatic way to see it is as a sea of virtual particles. For infinitesimally brief moments, pairs of particles and antiparticles can borrow energy from nothingness, erupt into existence, interact with the universe, and then annihilate each other, paying back their energy debt before reality can notice they were there. This isn't science fiction. This quantum foam is real. We can measure its effects in our labs, like the way it subtly shifts the energy levels of atoms. So, a theoretical physicist sits down and asks the obvious question, okay, let's calculate the energy density of this quantum foam. How much energy is there in this background hum? You list all the known quantum fields. You calculate the zero-point energy for each one. And you sum them all up. Technically, the sum is infinite. But physicists have a standard procedure for this. You assume that our current theories break down at some very high energy, like the Planck energy, where quantum gravity takes over. So you sum the energies up to that cutoff point. It's a reasonable, back-of-the-envelope calculation. You do the math. You check your work. And you arrive at a number for the energy density of the vacuum. That number is 10 to the power of 120 times larger than the number the astronomers measured. I need you to understand what this means. This isn't a small discrepancy. It isn't being off by 10%. It isn't being off by a factor of 1,000, or 1,000,000, or 1,000,000,000. A 1 followed by 120 zeros is a number so vast it defies physical analogy. There are only about 10 to the 80 atoms in the entire observable universe. This number is a trillion, 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 trillion times bigger than that. The mismatch between our best theory and our best observation is a 1 with 120 zeros after it. This is, without exaggeration, the single worst theoretical prediction in the history of science. It's like hiring a team of the world's best architects to build a doghouse, and they deliver a structure the size of the solar system. Something is profoundly, fundamentally, catastrophically wrong. Now, any sane person, including physicists for many years, would ask, can't you just ignore it? Define that insane background energy as zero and only measure the changes on top of it? In the world of quantum mechanics, that's exactly what we do. It's a trick called renormalization. In a particle accelerator, you only care about the change in energy when two particles collide. You don't care about the absolute energy of the vacuum they're flying through. You can set your sea level to whatever you want. It doesn't change the height of the waves. This trick works perfectly for all the forces of nature, except for one. There is one force in the universe that cannot be fooled. One force that acts as a cosmic auditor, demanding to see the complete, unredacted books. That force is gravity. According to Einstein's general relativity, all forms of energy and mass are two sides of the same coin, E equals mc squared. And all energy warps the fabric of space-time. Gravity doesn't care if the energy is in a star or in the quantum jitters of the vacuum. It couples to the absolute value. The vacuum's enormous bank account is real money to gravity. Every last virtual particle makes a deposit, and that deposit has gravitational weight. If the quantum prediction were correct, the gravitational repulsion of the vacuum would have been so overwhelmingly powerful that the universe would have flung itself apart in the first 10 to the minus 43 seconds of its existence. Atoms would never have formed. Stars would never have ignited. We would not be here. The fact that you are watching this video is the most direct proof that this calculation is wrong. And it gets even worse. This isn't just a one-time accounting error at the beginning of time. Over the universe's history, major financial events have happened. When the universe was a fraction of a second old, it cooled enough for the Higgs field to turn on, filling the universe and giving particles mass. This phase transition should have changed the vacuum energy by a colossal amount. Think of it as a multi-trillion-dollar deposit into the vacuum's bank account. A few microseconds later, another transition happened. Quarks became confined inside protons and neutrons. Another massive deposit. The final balance sheet of the vacuum today should reflect all these huge historical transactions. It should be enormous. Instead, the final number we observe is so close to zero it's absurd. This means that somehow, the initial, mind-bogglingly huge quantum energy must have been cancelled by some other, equally huge number, to a precision of 120 decimal places. And then, every time a new phase transition happened, some new, miraculous cancellation occurred to keep the total near zero. It's like a company having trillions in revenue and trillions in expenses, balancing out to a profit of a single penny, every single year, by pure chance. Nobody believes in that kind of luck. Something must be enforcing this cancellation. So, what is it? What could possibly solve the most profound paradox in modern science? Here are the leading suspects. Suspect number 1, the elegant alibi, a hidden symmetry. The dream solution, the one physicists prayed for, was an elegant, hidden principle of nature. The most promising candidate was a beautiful idea called supersymmetry, or SUSY. It proposes that the universe has a deeper, hidden layer of symmetry. For every matter particle we know, like an electron, which is a fermion, there exists a corresponding force-carrying superpartner particle, a selectron, which is a boson, and vice versa. Here's the magic trick. In the quantum vacuum, fermions, like electrons, contribute positive zero-point energy, while bosons, like photons, contribute negative zero-point energy. If supersymmetry were perfect, for every particle type, its superpartner would exist with the same mass, and their contributions to the vacuum energy would cancel each other out perfectly. Like a positive one and a negative one. The ledger would be flawlessly balanced at zero. Problem solved, with mathematical beauty. Except there's a problem. A huge one. If these superpartner particles existed with the same mass as their standard model counterparts, we would have found them ages ago. We've spent decades and billions of dollars smashing particles together at the Large Hadron Collider, and we have found absolutely nothing. No selectrons, no squarks. So if SUSY exists at all, it must be a broken symmetry in our low-energy universe. This means the superpartners are much heavier. And the moment you make them heavier, their masses no longer match, the perfect cancellation is ruined, and the vacuum energy problem comes roaring back, still wildly too large. Suspect number 2, the dynamic solution, it's not a constant. Maybe we're making a fundamental mistake. Maybe the energy of space isn't a constant at all. Perhaps it's a dynamic entity, a new quantum field that has been changing over the 14 billion-year history of the cosmos. This category of ideas is called quintessence. Picture a marble slowly rolling down a very long, very, very gentle energy hill. Early in the universe, the field was higher up the hill, and its energy value was large. Over cosmic time, it has been slowly rolling down, its energy decreasing. Today, it has slowed almost to a halt at the bottom of the hill, giving us the tiny value we observe, which just mimics a constant. This is appealing because it's dynamic. But it has its own problems. The hill has to be impossibly flat for the field to roll this slowly. The mass of the quintessence particle would have to be fantastically light, lighter than any known particle, which makes you wonder why we haven't detected its influence elsewhere. And it raises a new fine-tuning issue, the coincidence problem. Why is it that right now, in this specific cosmic epoch, the energy density of this quintessence field is of the same order of magnitude as the energy density of matter? It seems like a wild coincidence. Suspect number 3, the radical plea, gravity is not guilty. This is where things get really wild. What if the entire premise is wrong? We've been assuming that QFT's vacuum calculation is real, and that gravity is the problem for not handling it correctly. But what if gravity simply doesn't care? What if, for some deep reason, gravity is fundamentally blind to the constant, background energy of the vacuum? Ideas like sequestering or degravitation or unimodular gravity explore this. They propose modifications to Einstein's theory. Perhaps gravity only responds to changes in energy, not the absolute background value. Maybe spacetime is like an incompressible fluid. It can ripple and wave, but you can't change its overall background pressure. This is hugely appealing because it dissolves the problem at its root. But it's a monumental step. For a century, general relativity has passed every test we've thrown at it. To modify it is to question the foundations of our understanding of the universe. So far, no one has built a completely consistent, problem-free theory that does this without breaking something else. Suspect number 4, the controversial verdict: we won the cosmic lottery. And now we arrive at the most debated, most profound, and to some, most infuriating idea of all. The anthropic principle, powered by the concept of the multiverse. What if there isn't just one universe with one set of physical laws? What if there's an unimaginably vast collection of universes, a multiverse, where the fundamental constants of nature, including the value of the vacuum energy, are different in each one? This idea isn't just pulled from thin air. It's a potential consequence of string theory, our leading candidate for a theory of everything. String theory doesn't predict one universe, but a landscape of maybe 10 to the 500 possible universes, each with its own stable vacuum and its own laws. If that's the case, then in the vast majority of those universes, the vacuum energy would be huge, the natural value predicted by QFT. And those universes would be utterly sterile. They would either fly apart in an instant or collapse in a flash. Dead on arrival. No possibility for complexity, no galaxies, no stars, no chemistry, no life. So where would creatures like us, made of atoms and capable of asking questions, find ourselves? We could only exist in one of the vanishingly rare universes where, by pure dumb luck, the vacuum energy just happened to fall into the microscopically thin sliver of values that allows structure to form. It's not that the value is special in a fundamental sense. It's special from our point of view because we couldn't live anywhere else. It's a form of cosmic selection bias. Physicist Steven Weinberg, years before dark energy was discovered, used this exact logic to predict that if the vacuum energy was ever found, it would have to be very small, close to the value we now measure. It remains one of the few successful, non-trivial anthropic predictions ever made. To many scientists, this is the only plausible explanation. To others, it feels like giving up on physics, replacing a discoverable law with a cosmic lottery we just happen to win. It is the center of the biggest philosophical battle in physics today. Now, let's step away from the theory and go back to that coffee cup. I want you to truly feel the impossible fragility of this moment. Imagine you could reach out and turn a dial on the universe labeled vacuum energy. Let's turn it up by just a factor of 1,000. Remember, this is still 117 orders of magnitude smaller than the quantum prediction. It's a tiny, tiny nudge. In that new universe, the repulsive force of dark energy would have overwhelmed gravity from the very beginning. The primordial soup of particles that emerged from the Big Bang would have been blasted apart. No clumps would form. Gravity would never get the chance to pull matter together into the first galaxies, the first stars. That entire universe would be a cold, thin, ever-expanding mist of lonely particles. Utterly dark. Utterly sterile. For eternity. Okay, reset. Let's turn the dial the other way. Let's make the vacuum energy large and negative. Now, instead of a push, you have an all-powerful crush. The fabric of space-time has a violent, inward tension. That universe doesn't even make it a billion years. It expands for a brief moment, and then immediately recollapses in a fiery big crunch, a cosmic abortion snuffed out before planets could form or life could possibly evolve. Our number, the one we actually measure in our universe, sits on an impossibly thin knife edge between these two catastrophes. A razor-thin boundary where complexity is allowed to bloom. Where the cosmic push and the gravitational pull can wage a balanced, multi-billion-year war that gives galaxies time to form, stars time to forge heavy elements, and life time to emerge and wonder about it all. The silent, calm, peaceful nothingness in your coffee cup is a lie. It's a miracle. Its placid appearance is underwritten by a cosmic cancellation of incomprehensible precision. Nothingness isn't just an absence. It is a physical property, a choice the universe had to make, and it had to get it just right. We started with a simple question: why doesn't empty space tear us apart? And after this deep dive, the humbling, honest answer is, nobody truly knows. But in asking the question, we have exposed the deepest, most profound cracks in our current understanding of reality. Is the answer an elegant, undiscovered law of nature, a new symmetry like Susie waiting just beyond our reach? Is it a sign that we need to rethink the very nature of gravity itself? Or are we simply the unlikely inhabitants of a lucky bubble in a vast, chaotic multiverse? If it turns out that dark energy is a true, unchanging cosmological constant, then the future of our universe is sealed. The cosmic acceleration will continue forever. In the distant future, every galaxy not gravitationally bound to our own will slip beyond a cosmic horizon, their light stretched into oblivion, never to be seen again. The night sky will slowly empty, until only the stars of our own local galaxy remain in an endless, cold, dark void. The gentlest of energies, the ghost in the machine, will win in the end. Understanding why that ghost is so gentle isn't just an academic puzzle. It may be the single most important clue we have to the ultimate nature of our reality. So, while you let the weight of the universe's biggest mistakes sink in, click the video on your screen right now. It's another deep audit of reality's most baffling secrets, and watching it tells the algorithm that you have excellent taste. It really helps us keep questioning the cosmos. Now I have to put you on the spot, after hearing all the suspects, which idea resonates with you? Are you on Team Symmetry, believing there must be a beautiful, undiscovered physical law? Or are you on Team Multiverse, concluding that we must have just won the cosmic lottery? Tell me your verdict in the comments below. I'm fascinated to see where this community lands. And finally, if you believe that the most exciting questions are the ones we can't yet answer, if you love confronting the boundaries of human knowledge, then make sure you subscribe and ring that notification bell. We audit another piece of the universe every single day,